Hello everybody, welcome back to Physics 425. What I want to talk about today is some practical considerations in how you would actually operate a dilution refrigerator. So last time we talked about the cooling power that we would get out of a dilution refrigerator, and remember, what we imagined is that we have a mixture of helium-3 and helium-4, and we cool it enough that this phase separation occurs. So we have a dilute phase of a small concentration of helium-3 atoms in helium-4, and that's on the bottom. And then on top of that, we have a concentrated phase, which is almost pure helium-3. And we imagine this as kind of analogous to evaporative cooling. If we could remove helium-3 from the dilute phase by a pump or some other mechanism, then helium-3 from the pure phase on top would cross that phase boundary and enter into the dilute phase. And when it crossed that phase boundary, that was analogous to evaporation, and the cooling power was determined by the change in enthalpy that we got as helium-3 crosses that phase boundary. And it'll also be dependent on how fast we circulate the helium-3. So if we increase the circulation rate so that n dot increases, then we get a higher cooling power. Okay, when we did our analysis, we had to calculate what the enthalpy would be of the dilute phase and the concentrated phase, and that was a bit of work, but once everything was done, what we found is that for a typical dilution refrigerator, the cooling power might be around this 83 times n dot, the molar circulation rate, times T squared. And if we assumed some typical circulation rates, n dot in moles per second, and a certain heat load that was being absorbed by our mixing chamber, which contains our mixture with the phase boundary, then we could calculate a base temperature, and it's on the order of, around 10 to 20 millikelvin or something like that. Okay, good. So that's a quick little review of what we talked about. And so the operation of a dilution refrigerator. What I'm going to talk about is the operation of a wet dilution refrigerator. And what wet means is that we're going to use cryogenic liquids to pre-cool the system. I'll say something briefly about dry dilution refrigerators at the end. Okay, so first, let me show you a picture of a dilution refrigerator. So this picture comes from Wikipedia. And we'll talk about each of these components in a few different steps, but the first thing that I want to imagine is we're going to try to pre-cool our system. And so the first step is to fill liquid nitrogen in this region, and that's going to cool everything down to 77 Kelvin. So you might fill your liquid nitrogen and leave it overnight to wait for everything to get to 77 Kelvin. Once that's happened, you can fill the next compartment with liquid helium, and we can pre-cool everything to 4.2 Kelvin. In fact, in one refrigerator that I used, what we did is we put nitrogen into the helium space, let everything go to 77 Kelvin, then come back and you pressurize the dewar to push the nitrogen out, and once it's empty, then you put your liquid helium into that space. Okay, so step 1 is fill liquid nitrogen and liquid for helium dewars. Okay, you'll notice that there's an interior vacuum space here. And so that interior vacuum space contains the main components of the dilution refrigerator. And so what I want to do is I'm going to show you an image that just highlights everything that's inside that interior vacuum space that's surrounded by liquid helium. And so here's our liquid helium bath on the outside of this vacuum space, and so it's at 4.2 Kelvin. Okay, and so inside we have a bunch of stuff. We have our mixing chamber at the bottom, and then we have a series of heat exchangers. There's something called a still that's above the mixing chamber, and there's something called a 1K bath or a 1K pot. And so let's talk about each of these things separately. Okay, so 2 is the helium-4 from the outside bath fills a 1K pot via a fill line. Okay, and so here is our fill line. It's just a narrow capillary, and this is our 1K pot or our 1K bath. And so to fill the pot, what we're going to do is we're going to turn on a pump. And so this goes to a pump. And so in this previous picture, you can see that there is a pump for the 1K bath. And so when we start pumping on this little pot, the reduced pressure causes helium from the outside to fill through this impedance, which is a long capillary, and we get some liquid filling up this 1K pot. Because we're pumping on it, the vapor pressure above that liquid is reduced, and we get some cooling just by evaporative cooling. So the liquid helium-4 in the 1K pot is pumped so that it reaches a temperature of, maybe between 1.2 and 1.5 Kelvin. Let me just remind you of these vapor pressure versus temperature curves. And so here's helium-4 is this orange line, and as we reduce the vapor pressure, the temperature comes down. And so we might operate our 1K pot at whatever this pressure is and get to about 1.5 Kelvin. Okay. And in step 3, what we're going to do is after we've cooled our pot to about 1.5 Kelvin, is we're going to let the helium-3, helium-4 gas mixture into the dilution refrigerator. So of course, helium-3 is very expensive, and so you never just get rid of it. So all of this mixture of helium-3 and helium-4 gas is stored in storage vessels at room temperature. And so when you're ready to let this into the fridge, you open some valves, and that allows the mixture to flow into the refrigerator. And so what we do is we open some valves, and the mixture enters through here. And what it does is it has to pass through a series of heat exchangers. And so these red things are heat exchangers. It's connected to the outside of the 1K pot. So the outside of this heat exchanger is cooled to 1 Kelvin, and as the gas mixture passes through this small narrow tubes that are connected to the heat exchanger, it cools as it enters into the refrigerator. Okay. So the mixture cools to about 1.5 Kelvin, which is enough to cause the gas to condense into liquid. So this liquid is going to be a homogeneous liquid. So there is no phase separation. Yet. So let me remind you of this phase diagram that we had. Temperature on the vertical axis and concentration of helium-3 on the horizontal axis. And so if we're at a temperature initially of about 1.5 Kelvin, then we don't get into this phase separation region. And so what we just have is a liquid with a uniform distribution of helium-3 and helium-4 throughout. Okay, so next we start pumping on what's called the still of the dilution refrigerator. I'm going to go back and look at what the still picture looked like. So what we've got now is we've cooled our mixture enough that we have liquid filling the mixing chamber, and then also filling this tube that goes up along here, passes through some other heat exchangers, and then we got some mixture that's also condensed inside what is called the still. And above the still is a big wide tube, and that big wide tube is connected to a helium-3 pump, and that is used to pump on the vapor above the still and then reintroduce that vapor back into the dilution refrigerator. Okay? So that's the idea now, is we're pumping on this homogeneous liquid, and what will happen is the pumped mixture cools via evaporative cooling, and because we have helium-3 in that mixture, its vapor pressure versus temperature curve is different, and so we can actually get to lower temperatures, and we can get to low enough temperatures to start this process of the phase separation. So we can get to temperatures that are low enough to cause phase separation to occur. One thing to note is that you have to start with the right concentration of the mixture. You have to have the right ratio of helium-3 and helium-4 so that that phase separation occurs within the mixing chamber. If you have either too little or too much, the ratio is a little bit off, then the phase separation might happen outside of the mixing chamber and you won't get good performance. So we need to select the ratio of helium-3 to helium-4 such that the phase separation boundary occurs inside the mixing chamber. So what we have is our mixing chamber. This is connected to the still. And so actually what will happen is we'll have a pipe that goes down like this, and inside here we're going to have our phase separation boundary, and then we're going to have the dilute phase down here. So that's a small fraction of helium-3 in helium-4, and then we have the concentrated phase here. And so this is, at base temperature, this is nearly pure helium-3, and this might be about, I don't know, 6.6% helium-3 in helium-4. And then we also have, because we're circulating helium-3, we're reintroducing helium-3 to the concentrated phase after it's pumped out of the still. Okay, but if you don't have the ratios quite right, this phase boundary might occur, somewhere up the still, the line, the tube that goes up to the still or something like that. And then what you would have to do is you'd have to adjust the ratio of your mixtures. Okay. So we can cool the mixture to a temperature that is about 0.5 Kelvin by evaporative cooling, so just by pumping on the still. And this temperature is low enough that what will happen is we will enter, so if we got to say 0.5, we'll enter this phase separation region where we'll have our concentrated and dilute phases, where the dilute phase might be something like 25% helium-3 and helium-4, and the concentrated phase might be somewhere around 80% helium-4. Sorry, I got that wrong. The concentrated phase would be about 80% helium-3. Okay. So I want to make a note that when we are pumping on the still, we are removing primarily helium-3. So that might seem counterintuitive because what we have is a mixture of helium-3 and helium-4, and so why, when we pump on the still, is it primarily helium-3 that's being removed? This is because the vapor pressure of the helium-4 component is very low. And so, I think I want to show this picture here. So if we got to some low temperature below 1 Kelvin, then what we would have is a certain vapor pressure of helium-3, which is appreciable, but the vapor pressure of the helium-4 component would be really, really small compared to that. You know, roughly it might be 2 to 3 orders of magnitude smaller. And so that means the vapor that you're pumping on above the surface of the liquid in the still is almost exclusively helium-3. In fact, what we're going to do is we will actually need to apply heat to the still. Why? Well, the purpose is we want to raise the vapor pressure of the helium-3 component such that the helium-3 circulation rate is relatively large. So remember, that the cooling power was Q dot is equal to, it was about 83 N dot T squared. And so this is the molar circulation rate of helium-3. So if we can make a large N dot for a given heat load, we would have a low temperature. And so this is the temperature of the mixing chamber. So let's put MC. This is mixing chamber temperature. And so what we want to do is we want to raise the temperature of the still so that if we increase the temperature a little bit, then we can get an increase in the vapor pressure of the helium-3 so that when we pump on that vapor pressure, we can increase our circulation rate. Okay? We don't want to increase the temperature too much because then we'll start introducing too much helium-4 into the gas that we're circulating. Okay, so we can't make the still too hot because that will raise the helium-4 vapor pressure such that we're not circulating, let's say such that we are no longer circulating almost pure helium-3. Okay, And so in this picture, there is a heater on the still. So it's just a resistor, and you pass some current through that resistor, and you apply the right amount of heat so that your still temperature is typical. A typical temperature might be about 0.7 Kelvin. So a typical still temperature is approximately 0.7 Kelvin or 700 millikelvin. Okay, good. So now I want to do a little bit of an aside. And so I want to talk about osmotic pressure briefly. So, here's the slide that I was looking for, osmotic pressure. So I want to imagine that we have a tube that's bent into the shape of a U, and so we fill the tube initially with water, but then there's a membrane here, and that membrane allows water to pass through it, but not solid substances. Okay, and so initially the level of water on the two sides of our tube are the same. And then we dump some salt, or sugar in this case, on one side. And so that sugar dissolves in the water. And what we observe is that some of the pure water on the right-hand side of the tube flows through the membrane and to dilute the sugar that was added on to the left-hand side. And so as a result of this, we get a difference in height between the two sides. And so this might be a height difference of delta H. And we could calculate the pressure difference that results from the water that has flowed from the right half of the tube into the left half. And so what we could do is we can associate a pressure with with the solute of sugar added to the water on the left-hand side. And so that pressure is called an osmotic pressure. So in fact, I think what I'm going to do is, I probably got ahead of myself here. I'm going to make this aside on the next slide. I think the slide that I skipped here is just talking about at the temperature of the still is about 0.7 Kelvin. We mainly remove helium-3 atoms, but we don't want the temperature to go too high because that will add helium-4 into the circulated gas. Okay, so now we can do our aside, which is osmotic pressure. Okay, so the osmotic pressure has a symbol capital Pi. And there's an empirical expression that says the osmotic pressure is equal to some dimensionless constant, which we're going to call I, times the molar concentration of the solute. In our example, it was sugar added to water, so sugar is the solute, and then it was equal to R times T. Okay, so this molar concentration is the number of moles of the solute divided by V, and so this is number of moles of solute. And notice that this looks like an ideal gas. This looks like the ideal gas law. So this is similar to the ideal gas law. PV is nRT, or P is equal to N over V, which would be the molar concentration times RT. So it's similar except for the fact that I is some dimensionless constant. So this is a dimensionless constant, and it's called the Huff Index. Typically, this index is, some constant close to 1. Okay, and so I'm just going to redraw the picture that was on the slide that we looked at. And so here's our membrane. And so this membrane allows water to pass through, but not sugar. Okay, and so here's our water level. And then we add our sugar. And what happens is we get a difference in the height on the two sides. And so this level comes down, and this level goes up. And so in here we have just pure water, and over here we have sugar water. And so here's our height difference, delta H. And let's imagine that our tube has a cross-sectional area A. Okay, so if we color our column blue, what we could do is we could calculate the weight of the shaded column. So that would be M times G, but we could write M as the volume of the column times the density. And that volume would be A times the height difference. And if we divide by the cross-sectional area A, we calculate that pressure difference. And so let's do that. So the weight of the shaded column is mg, which is rho, the density of water, times the volume, which is A times delta H, and then we still have our factor of G. And so therefore the pressure difference is delta P is mg, the weight, divided by the cross-sectional area, which is rho g delta H. And at equilibrium, what we would have to require is that this pressure difference, due to the extra water on the left-hand side of our tube, has to balance with the osmotic pressure. And so our rho g delta H has to be equal to the osmotic pressure, which would be the molar concentration of the solute times RT. This is assuming that our index I is equal to 1. And so therefore delta H, the height difference that you would expect from adding a certain amount of sugar, would be equal to the molar concentration times RT divided by rho g. Okay. So that's a little bit on osmotic pressure. And so what does that have to do with our dilution refrigerator? So here, this picture requires a bit of explaining. So on the left-hand side, I have the mixing chamber. So here I have my mixing chamber and I have the still. So it's just a zoomed in view of the mixing chamber and still filled with our helium-3, helium-4 mixture, and we imagine we've cooled it so that there is a phase boundary in the mixing chamber. The dilute phase is the phase that's on the bottom, because that's the one that has helium-4, which is denser. And so it's like 6% helium-3, 6.6% helium-3, and helium-4. And on top of that, we have the concentrated phase, which is nearly pure helium-3. The dilute phase is connected to the still by a long tube that passes through the concentrated phase, and then its opening is within the dilute phase. And so that dilute phase goes up this tube and then also into the still. And then we pump on the vapor that's above that still, the liquid in the still. The picture on the right-hand side is the same thing, but what they're showing is a direct connection between the mixing chamber and the still. And so they're drawing it as if the dilute phase is on top and then the concentrated phase is on the bottom. And so that enables them to draw this picture where you have a direct tube that just connects the dilute phase of the mixing chamber to the still. And then you circulate, you remove helium-3 from the still and then reintroduce it to the concentrated phase. Okay, so these are two versions of the same picture. The one on the right is just convenient for thinking about the circulation of helium-3. So I'm going to try to reproduce that picture. And so what we have is something like this. And so here's our still at 700 millikelvin. And here's our mixing chamber. And so this might be around 10 millikelvin in equilibrium. And I'm going to draw this like it is on the slide, as if this is pure helium-3 on the bottom. So this is our concentrated phase. And then we have our helium-3 mixed in helium-4, and so that's our dilute phase on top. And that dilute phase extends up into the still to some level, and then above the surface of that liquid we have vapor, and that vapor is being pumped and circulated. Okay, and then let's say below we have our concentrated phase of pure helium-3. Okay, so what we could do is we can treat, just like we had sugar and water, we can say that in our dilute phase we have some helium-3 dissolved in helium-4. So if we treat the helium-3 in the dilute phase as the solute in helium-4, then we could say that in the mixing chamber we have an osmotic pressure that's equal to the molar concentration of helium-3 in the dilute phase of the mixing chamber times RT, where T is going to be the mixing chamber temperature. And in the still, we have an osmotic pressure that's equal to the molar concentration of helium-3 and helium-4 in the still times R times the still temperature. And so in equilibrium, we require that these two osmotic pressures are equal. And so if you set these two things equal to each other, the factors of R cancel, and it must be that the concentration in the mixing chamber times the mixing chamber temperature must be equal to the concentration in the still times the still temperature, or the concentration of helium-3 the concentration of helium-3 in the still is equal to the concentration of helium-3 in the mixing chamber times, let's write it as molar concentration just to have a consistent notation. Okay, times temperature of the mixing chamber divided by the temperature of the still. So if T mixing chamber over T still is equal to something like 10 millikelvin divided by 700 millikelvin, then that's about 1/70. Then if the concentration of helium-3 in the mixing chamber is, say, 6.6%, then the concentration of helium-3, and the concentration of helium-3 in the mixing chamber is 6.6%, then the concentration of helium-3 in the still is something like 0.1%. Okay. Sorry, I wanted to, let me see if I can add a slide here. Okay, good. So, now let's imagine if we remove helium-3 atoms from the still using a pump. Then we lower the concentration of helium-3 in the still and create an osmotic pressure difference. That pressure difference between the mixing chamber and the still would be given by this difference. So if we lower this molar concentration, then the pressure, osmotic pressure in the mixing chamber is higher, and that's going to drive helium-3 up the tube that connects it to the still, and that promotes this circulation of helium-3. And so this pressure difference drives helium-3 from the mixing chamber to the still. But of course, if we take helium-3 out of the mixing chamber and push it up to the still, then we have a lower concentration of helium-3 in the dilute phase of the mixing chamber. And that's going to cause helium-3 from the concentrated phase to cross the phase boundary and enter the dilute phase, and that's where our cooling comes from. But now, the molar concentration in the mixing chamber is too low, and helium-3 from the concentrated phase crosses the phase boundary and enters the dilute phase. This process gives us the desired cooling. In which Q dot is equal to the rate that helium-3 crosses the phase boundary times this enthalpy difference between the dilute and concentrated phases. Okay, good. So the last step is, or the last thing to note, I think this is step 6 in my list. Helium-3 removed from the still is cooled via heat exchangers and reintroduced to the concentrated phase. I.e. the pure liquid helium-3. So what we do is we pump on the vapor above the still, which is pure helium-3, and that is recirculated back into the fridge. So it comes back down here. It first passes through the 1K pot. So, you know, when it leaves the fridge, it ultimately goes through a series of pumps that are at room temperature. And so that gas warms up to room temperature and then it comes back down into the fridge. The first thing is that gas is going to pass through a heat exchanger that's connected to the 1K pot, so it cools to 1K. And then there's some impedance here so that the gas doesn't enter the fridge too quickly. It has to go slowly so it has time to cool. And then it passes through heat exchangers that are connected to the still. And so it cools to about 0.7 Kelvin. And again, there's another impedance that slows the flow down. And then these are a series of heat exchangers that get colder and colder as we approach the mixing chamber. And so by the time that the helium-3 is reintroduced to the mixing chamber, the concentrated phase, it's already pre-cooled, and so it's not adding too much extra heat to the refrigerator. Just as a side note, if you were really going for the ultimate lowest possible base temperature, you wouldn't circulate the mixture back into the fridge. You would just pump it out and store it at room temperature, and you can run this as a single shot where you get the lowest possible base temperature by eliminating the heat load caused by the reintroduction of helium-3 back into the mixing chamber. But if you do the circulation method, that allows you to run the fridge basically indefinitely, and you can maintain a temperature near 10 millikelvin for days or weeks, or as long as your experiment is required to run. Okay, and so we can run the dilution refrigerator continuously for long periods of time. Okay, and so here's a picture of on the right-hand side is a photograph of an actual dilution refrigerator. So there's the mixing chamber on the bottom. These are heat exchangers that cool the helium-3 as it is reintroduced after being pumped out of the still. And then there's the still. This thing is the 1K pot. I can't see the fill line, but somewhere there's a fill line that allows helium-4 from the surrounding bath to fill that 1K pot. The last thing I wanted to make just a note of is that there are now systems that are called dry dilution refrigerators. The actual dilution refrigerator part is the same, and so all of the components of the dilution refrigerator are the same. Mixing chamber, heat exchangers, still with the still heater. But what it doesn't have is it doesn't have a 1K pot, and it doesn't have liquid helium surrounding the dilution refrigerator. Instead, a cryocooler is used as a pre-cooling apparatus. So two-stage pulse tube refrigerators are capable of reaching temperatures of about maybe 2 Kelvin at the base temperature at the second stage. And so that's enough to pre-cool your refrigerator and the mixture as it's entering the refrigerator so that you get the initial phase separation, and then you can start pumping on the still, and you can bring the still to its 0.7 Kelvin, and then the rest of the operation is the same. What's nice about this design is that you aren't required to have very expensive cryogenic fluids to initially cool your system down. And so if you were purchasing a new dilution refrigerator for your lab, you might give some serious consideration to one of these dry systems. A drawback to the dry system is that the pulse tube cryocooler can introduce or does introduce some vibrations into your system. And for some experiments, that might be undesirable. And in that case, if you needed a very low vibration system, you would revert back to a wet dilution refrigerator that uses cryofluids to do the initial cooling. Okay, thank you very much, and I will see you next time.